The mechanical force could be of different kind. And in this example, we will simulate the force caused by the electric current interaction. Here is the long solenoid carrying electric current. This is the winding. You can see the cross-section of the solenoid. And our task is to calculate the stress distribution in the solenoid. The current interaction, if we take a look at the single lobe of the solenoid, the current interaction is ruled by the Ampere's force law. In short, the force is in direct proportion to the current's product and in inverse proportion to the distance between the current's elements. And the best way to calculate the magnetic force is to perform the magnetic analysis. So I will start QuickField. Let me show you the problem properties. This is the magnetostatics problem, and the model class is Axisymmetric. Axisymmetric means that we will simulate only the upper half of the cross-section, and this would be the axis of the rotation. Now this is the geometry model. It's a small portion of the very long solenoid. So in fact this is only the small part. Here we have the two blocks, the coil, and the coil is carrying the electric current. And we have the air block. And the result of the magnetic simulation is the magnetic field distribution. I will switch on the column map of the flux density and the vectors of the flux density. So we can have the magnetic field, we have the electric current, and there is the magnetic force acting on the current elements. And we can measure this force if we select the coil if we select some element, some current, and follow to the integral, we can calculate the mechanical force acting on this element. So naturally our next task is to calculate the stress distribution in the solenoid. To calculate the stress distribution, I need the stress analysis problem. So I will create the new problem and call it stress. I should choose the problem type, the stress analysis, and I should choose the model class, the Axisymmetric. Now I would like to automatically transfer the forces from magnetic to stress analysis problem. To do so, I should choose the same geometry model in both problems. So in stress analysis problem, I will use the geometry model, the same geometry model that I used in magneto-static analysis, Coupl1. Now both problems share the same geometry model. And in this case, I can set up the link from magnetic to stress analysis problem. So I follow the stress analysis problem, open the problem properties, and follow to the links. Here I specify the link type, the magnetic forces. I choose the problem that contains the magnetic analysis result, this problem, and I add the link. Now my stress analysis problem is linked to the magnetic problem and imports magnetic force from the magnetic problem. Don't forget to specify material properties. In magnetic problem, we specified magnetic properties of the coil, and in the stress analysis problem, we should specify the mechanical properties of the coil. The Young's modulus is 107 and 5. Gigapascals, and this coefficient is 0.33. I will not calculate the stress distribution in the air, so I simply open the block properties and specify nothing here. I have a very long solenoid, so there is no axial displacement, because this same part present here and here on the left and on the right. So no axial displacement here. Now let's simulate the mechanical problem. Here you can see the result. I will zoom out so you can understand better. This was the original cross-section of the solenoid, and this is the deformed shape of the solenoid winding. Again, I can adjust the field picture and switch on the stress distribution color map and the vectors of displacement. So you can see the winding is pushed outside by the magnetic forces caused by the current flowing in the winding.